Okay, before I start. All right. Okay, hello everybody. Here in sunny Israel. I was about to say in sunny California because it's where I live. All right, that wasn't funny. I'm not very funny. That's why I'm no longer a comedian. Okay, so let's talk about Angular, the blockchain, and you. Before I do that, though, I'd really like to say a thank you to the 500 Tech team, the State of Israel, all the speakers, especially Pascal, because he is the one who's responsible for me putting in all the funny GIFs that you're about to see. And a special thank you to Nur, who really made me feel like home. Okay. So who am I? I'm Ari Lerner. I wrote a couple books. If you come up to me after my talk, I'll give you a discount code if you want any of those. This talk specifically is going to be part theory, pretty theory heavy, but we will get to code at the end of the talk. Okay, so why are we talking about the blockchain at an Angular conference? Well, I happen to think that Angular itself brought a revolution in web development, and I think the next revolution of the web is going to be powered by the blockchain. And there's a lot of links up there from people who are more reputable than I am, who also agree with me. So what specifically are we doing today? Today we are going to talk about building our own cryptocurrency and visualizing it using Angular. I think this is the part where I show you the demo. Hopefully I started it. Hooray! Okay, so this is what we are going to be eventually building towards, where we can send some coins around, and we have our auto-updating application, just like you're used to when you build an Angular app. And that may have taken a little while because it's actually running on a local blockchain on my computer, and it takes 10 seconds for those blocks to be mined. If you don't know what that means, don't worry. That's the meat of the talk. Okay, so raise your hand if you've heard of something like Bitcoin or a cryptocurrency, like Litecoin or Dogecoin or Bitcoin or Metacoin, ngCoin, shekels. No one's raising their hand for shekels. You guys are all lying. Okay. I see how it is. I see how it is. All right. So Bitcoin itself, for those of you who didn't raise your hands and were not too shy to raise your hands, Bitcoin is a currency that is completely distributed on a peer-to-peer network that doesn't require a central authority to transfer wealth. And when I talk about wealth, I'm talking about the coins specifically. And we'll talk about that, why. So this enables us to get away from having to deal with banks and governance processes in the middle. There's no more middlemen with something like Bitcoin and cryptocurrencies. The blockchain itself is the thing that enables that. That's the thing that makes it possible. Have you heard of the blockchain? Raise your hand if you've heard of the blockchain. Some people are raising their hands who didn't raise their hands when they said they heard of Bitcoin. All right. Bitcoin itself is powered by the blockchain. So let's talk about what the blockchain actually is. When I talk about a blockchain, I'm really just talking about a publicly accessible ordered ledger of facts that is cleverly distributed across a peer-to-peer network and an untrusted nodes around the world with the ability to partially solve really hard computer science problems such as reconciliation and distributed consensus. Pretty simple, right? Okay. So why does the blockchain actually exist? Well, for one, we can run a worldwide trusted computer. We can run a worldwide trusted network of computers without a central authority. As I mentioned banks before, we can also do this with hosting. If you can run your entire application and not pay a hosting fee other than the transaction fees that your application requires. That's like AWS containers to the max, right? Okay, so we're going to talk about how this works. Let's peek under the hood. The three things that we are going to talk about specifically are how we get distributed in a peer-to-peer network, how the blockchain enables and incentivizes untrusted nodes to join the peer-to-peer network, and how it gets everyone to agree in the blockchain. So let's first talk about the, how the blockchain is distributed in the peer-to-peer network. But let's say that we have a couple computers. We have one in San Francisco, my house. We have one in maybe Guangxi and another in Sydney, Australia. How do we know? We don't control those networks. We don't control the internet from China to San Francisco. How do we know the information that we're going to get, that the computer in China is sending us quality information in California? We need some way of confirming that these interactions are actually the interactions that we expect them to be. So in order to do that, we need to talk about this thing called hashes. Raise your hand if you know what a hash is. Anyone want to try to describe it? Raise their hand. Okay, I'll do it. A hash is a function that can be, a hash function is a function that maps an arbitrary length input to a fixed length output. These are one-way functions. You can't de-hash something. Anytime that we put any value into a hash, we expect the same value to come out. It's a one-to-one function. So why would we do this? Because this allows us to cryptographically prove that data is real, prove that the data that we receive is the data that we expect. So what does a hash look like? Raise your hand if you know what a hash looks like. If you've used Git, you know what a hash looks like. So this is a SHA-1 hash of the string hello world. Let's say that we, the string input itself is in that input box, and the hash of that value is, the SHA-1 hash of that value is underneath it. If I change this input string by a single character, notice how the entire hash changed. What do you think happens if I delete that bang at the end of hello world? Yeah, it'll go back to the previous one. It's a one-way function, and SHA-1, although it does have some problems, is pretty good at making, guaranteeing that you do have a single input will always give you that guaranteed output. So if you've used Git, you've worked with this thing called Merkel Trees. The reason why we use hashes in the first place is so that we can sorry, I really like Bill Murray. Okay, that's not too difficult, right? Okay, so why do we use hashes? The reason we use hashes is so that we can build this really interesting data structure called a Merkel tree. The Merkel tree is a very powerful data paradigm about dealing with data. What a Merkel tree allows us to do is it allows us to store and hash a large amount of information. Let's say that we have a block that contains a few pieces of information, like let's say the sender and the to and the value and maybe the timestamp. If we want to guarantee safety on an untrusted peer-to-peer network, a Merkel tree thanks, Pascal. A Merkel tree gives us a way to verify that that piece of data is not being either like accidentally corrupted or intentionally maliciously corrupted. So let's say, using my example of we have a piece of data, let's say that we can split up this data in 4 blocks. The way that we build a Merkel tree, what we'll do is we'll first take a hash of each one of those of each one of those pieces of those chunks of the data, and then we'll concatenate, we'll strip them off into pairs, and we'll concatenate those, and we'll take a hash of those. And then we'll repeat that same process until we get to a single root node. This root node is called the Merkel Root. The Merkel Root, we use the Merkel Root in a lot of different ways. It's a very special part of the Merkel tree, and we'll talk about why in just a minute. This enables us to do something that is called Merkel proofing. I think that's really funny. I kind of want to say it again. We can Merkel proof. Thank you. So why does this matter? Why would we want to use a Merkel tree instead of just sending the raw data? Well, for one, it provides a way for us to, instead of sending the entire list of transactions or an entire like 32 terabyte ordered ledger of facts from 0 to 100 just to get involved in the Bitcoin network, what the Merkel tree allows us to do is it allows us to only transfer a very small amount of facts, and we can still provide the same guarantees that we can if we have the entire blockchain. The one crucial part about this entire flow is that we need a trusted way to get that root hash. So, how do we get a trusted root hash? So nodes can only accept, any node who's participating in the blockchain network, any blockchain network, will only accept a root hash from a trusted source that it can verify. So when I talk about a verified peer-to-peer network across the world, I'm talking about our nodes that have the ability to accept root hashes. So let's say that Bob has a root hash from Alice, and Alice is a friend, but she can be kind of a shifty friend. So he doesn't necessarily know if Alice is always telling Bob the truth. How can Bob verify? That's just getting out of hand. How can Bob verify that the information that Alice is giving Bob is true? Well, because Bob participates in a peer-to-peer network, what he can do is he can go ahead and ask a whole bunch of other friends like Charlie and Michael and Ari for little pieces of information, and Bob can then go ahead and reconstruct the Merkel tree from just any one of the branches, and if the root hash of Bob's Merkel tree matches the root hash that Alice's Merkel tree that Alice gave to Bob, then Bob trusts that hash. Otherwise, Bob throws it away and says, Alice, go get a life. You gotta start telling me the truth. So once that happens, the hash is accepted as the new root hash, and Bob moves on. So how does the blockchain incentivize untrusted nodes around the world to provide computing power to the blockchain? This is called mining. If you've ever heard of the blockchain or Bitcoin, you've heard of mining. What mining actually refers to, or mining does, is it gives a computer a part to play in the blockchain network. It gives a reason to play. So every node who's participating in the blockchain is trying to find the solution to a really hard math problem, one that's unguessable, or one that's you can't hack it because it's an unguessable problem. It's a provably unguessable problem. So I'm not really going to go too far in the details of how this works. However, you can check out my talk. I have all the source code in there, and I'm sure I'll tweet about it with the selfie that I took at the beginning. So just look for your lovely faces. This is what mining looks like in action. This is a very slow JavaScript miner that's running literally in the browser. So when we talk about mining, what we're talking about is just a bunch of hashes being generated compared to other hashes. So when a node successfully completes this and submits it to the network, and a quorum of nodes accepts and validates the new hash, all the nodes, that node will get rewarded. If we're talking about Bitcoin, then it will get rewarded with a Bitcoin. If we're talking about another blockchain, that node is rewarded with a token or a partial token. After that happens, every single node starts over and starts retrying and finding the new solution to the next unguessable problem. So mining gives everyone who participates in the network a reason to be involved. And not only do the the nodes who find the solutions are handsomely rewarded, but every node who participates is also rewarded. And the way that that works is through transaction fees. So users who use the network, users who submit operations or submit transactions pay a small transaction fee, and that's distributed to all the nodes who are participating in the blockchain network. Finally, let's talk real quick about consensus. Consensus is getting everybody to agree. How does a blockchain do that? Well, I walked through the Merkel Proof. That's how consensus is reached. Once enough nodes verify the state of a transaction in the blockchain, the entire blockchain is then moved forward. And this can survive network splits. It can survive provided that an attacker has less than 51% of the network. It can survive hack attacks. That sounds like it should be a band. Hack attacks. Okay. And finally, the consensus protocol requires that one CPU or GPU only gives one vote. That's how distributed systems are designed. Specifically, distributed peer-to-peer networks are designed to prevent any single computer or owner of computers to get too much power in the network. Okay, so what's next from Bitcoin? And where are the problems with Bitcoin? One major feature of Bitcoin that Bitcoin lacks is the ability to prove anything about the current state of the network. How many Bitcoins do I have right now is a really hard question to answer when you're participating in the Bitcoin network. The reason is because you need to download the entire history, every single transaction, in order to be made aware of every other transaction, whether or not you are participating in one of those transactions or not, or your computer or your account. So instead of focusing this talk entirely on Bitcoin, we're actually going to integrate our applications with the next version of Bitcoin, which is called Ethereum. Raise your hand if you've heard of Ethereum. Great. Ethereum itself is another network on the blockchain. We just walked through the example of using Bitcoin as describing what the blockchain is. Ethereum is just that same thing. It's nothing, we'll talk about the differences in just a second. There's some really nice enhancements that Ethereum introduced that are not in the blockchain. So, like, the blockchain itself is just an ordered ledger of facts. Remember that big orange slide? It's just an order of facts. Ethereum takes the idea that we have an ordered ledger of facts and maps it onto computer operations. So rather than necessarily just tracking transactions and keeping a log of those, the Ethereum network allows us to run operations in a distributed network and keep track of state, which we can't do in Bitcoin. It does this using the idea of smart contracts. So smart contracts, although it sounds a little complex, it's not really. They're just programs that live on the blockchain. These programs have the ability to send data from one account to another account. They can count votes. We have a lot of flexibilities. They create side effects, so you can have a cascading event in one smart contract that affects another smart contract, that affects another smart contract, that affects another smart contract. Smart contracts give us a lot of flexibility, and we have the opportunity to write that, and we'll write one here in just a few minutes. So what kind of things can we do in Ethereum, and what kind of things are being done with Ethereum? Right now, people are doing a lot. There's a lot of things that are happening, like media ownership is one of them. Crowdfunding is another one, and you don't need a central authority you don't need someone, what is that crowdfunding platform that just the name escapes me in a second? Kickstarter, that's what I was, yeah. So we don't need Kickstarter to take 30%. Rather, we can just host our crowdfunding where we set up a goal, and once that goal is met, the money is withdrawn from everyone who's funding a particular project, and is deposited directly into the project's owner. And we don't need that central authority. We can get around the banks. We don't need a middleman. Another thing that people are using Ethereum for is setting up really creative ways of handling governance across companies. So if you have a really complex company and you want to allow the members of your company to submit votes in a way that gives everyone a say about how the decisions and directions that the company takes, you can do that with a blockchain on Ethereum. We can provide, people are doing things with democracy, with like next generation democracy, where actually votes themselves are publicly verifiable and they're semi-anonymous, which means that you can actually run a true democracy on the blockchain. Okay, so enough talk. Let's talk about creating a coin. Okay, enough theory. There we go. Enough theory. Let's go ahead and create a smart contract. So we created a smart contract using a TypeScript language, a TypeScript-like language that was modeled after JavaScript with types, called Solidity. Solidity is a language that is built into Ethereum. It is not a part of our Angular application, although it can be, and in the demo it is a part of it, or the file is included in there. However, this is a completely different environment. So when I talk about the contract, I'm talking about the Solidity contract. When I'm talking about the services in Angular, I'm talking about TypeScript in our application. So in another file, let's go ahead and create our smart contract. The way that we do that is we use the keyword contract, and then we give the name of the smart contract that we want to make. Here we're going to make a coin called MetaCoin. In order to track state, MetaCoin allows us to create these things that are called mappings. Mapping is just like a JavaScript object. You can just say, I have a map that you have to declare the type that comes, that the key takes on. In this case, it's an address. And the value here, in this case, is an unsigned integer. These can be complex types. So if you have an account, you can create a struct in a smart contract that allows you to have more detailed information about what's kept in the value. So the last thing that we need in our smart contract is creating a constructor function. This constructor function will run once and only once for any time that this contract is enabled in the network. So this smart coin doesn't really do very much. It just keeps 10,000 shares of MetaCoin inside of this a single account and doesn't do anything with it. So rather than doing that, let's go ahead and add a function that enables us to get the balance for an address for a participant in the network. It's pretty simple, right? Oh, I can't bump up the font. Bump up the font. Wow, wow. Okay. Yeah, so just like JavaScript, we can address using the array function, using the array operator, the address of the mapping that we want to get the value from, that we want to get the value of. And that function, I think, is really readable. So how do we integrate our application with the blockchain? Or how do we integrate this contract with the blockchain? What we need to do is we need to use a tool. We need to compile our Solidity contract. We need to turn that into a machine-readable piece of data, and we need to send that up to our test network, or the real network. In this case, I'm running it on a test network on my local machine, so I'm not paying any ether to somebody for this talk, because, you know, it gets expensive. Okay, so the way that we can do that the way that we'll do that specifically is we'll use a tool called Truffle. Truffle itself does a lot of the hard stuff for us. The way that we compile that is by using the truffle compile command, and the way that we add this to the network is by using the truffle migrate command. I've already gone ahead and run this. So it's on the network right here. Okay, so let's get to the Angular part. How do we talk to Angular? How do we talk to the blockchain from Angular? It's actually not as hard as it sounds. What we can do is we'll create a service in Angular, and we'll create a service that manages the interaction between our application and the blockchain. This is, by the way, how we can get around hosting costs. We don't need a middleman because we can just send our data up to something like S3 and have the blockchain resolve our DNS address, which is pretty common. So anyway, we'll use this thing called Web3. Web3 is an RPC client for the network that we're running on. Ethereum runs all the Ethereum nodes run this RPC client. The test RPC client that I'm running runs it. And Web3 is a JavaScript version, a JavaScript module that allows us to talk over this RPC protocol. Okay, so we will create our Web3 service, and we'll keep a reference to the Web3 instance. So first what we need to do is we need to get a hold of a provider. This provider is running on my local machine, so I'm just giving it localhost. And then, like I said, we'll keep a reference to the Web3 instance. We can get, the reason why we keep a hold of that Web3 instance is so that we can get access to the accounts on this network, either the Ethereum network or our local network. These accounts, by the way, are just SHA hashes. They're just, I think, SHA-3 hashes. Okay, smart contracts. We can compile smart contracts using a tool called the Truffle Contract. The Truffle Contract allows us to just call these functions directly from our TypeScript out to the blockchain. This is really cool. What these smart contracts do is they will compile they'll compile the functions, they'll send them up to the blockchain, and they'll generate addresses. So actually what's going on under the hood when we call our contract is it's making an RPC call to a specific address in the blockchain. What that means is I can call any function that is written on any smart contract in the blockchain. So these are publicly accessible, publicly verifiable functions. So any function that I write, any other operator can see, and any function they write, I can interact with, that's like the next version of APIs. I'm sorry, I'm getting ahead of myself. Okay, so how do we hook up the two? All we have to do is set the provider that we're talking to, where the addresses are actually created from Web3 to our Metacoin contract. And in TypeScript, what we can do is we can just literally call that function. See get balance right there? That's the function that we wrote. Okay. So the last thing I'm going to talk about, and I have just enough time to cover, are events in Ethereum. So events themselves are super useful. They're really awesome. So how in the demo, did I send 10 Ether to the third address on my local box, and the balance updates in real time? Of course, as I said before, it takes the amount of time that it takes to register a transaction. In this case, I set it to 10 seconds, so it's obvious that it's actually taking time. Do you see the account update though, where it's 9980, in approximately 10 seconds, it will be 9970. How do we do that? Well, the way that we do that, or specifically the way that I did that, is by using the events in the smart contract. So for instance, one event that we might want to fire is when we might want to trigger an event that says, hey, a transaction has been completed. So in our Solidity contract, we didn't walk through this function, but all the way at the bottom of the function, you can see that there's an event that's called transfer. And that event that's called transfer sends a bunch of relevant information about that event. So we can listen for that in our client. We can listen for that event, an event called transfer, because a bunch of other events can get fired. And then we can just call get balance. And now we have a reactive front end. Does that sound familiar? Last thing, RxJS, right? RxJS, if you've ever written an Angular 2 and up app, you've probably used RxJS, or at least come across the term. It's a reactive framework written by Microsoft. The Metacoin service that we have in our application, simply when it calls get balance, it simply pushes the next value of which is the balance into our behavior subject. They're a perfect pair. Okay, so unfortunately I have 4 seconds, so I don't have time for questions here, but I'll be around the conference all day and around Israel until Tuesday. Cool, thank you.